project, we study strategic disclosure in research races. For academic research, there are two features that we want to emphasize here. The first is that the result of research is a public good. Once the result is published, everybody else can really use it and accomplish later results. And secondly, research is cumulative. Later researchers can use earlier published results and therefore stand on the shoulder of giants. And there are two questions that we want to study in academic races. The first is that what is the incentive to exert effort to provide such public good? Secondly, once a researcher has gotten an intermediate result, what is the incentive to disclose such a discovery so that later researchers can use it? To fix the idea, maybe let me use a problem that mathematicians face. In order to prove an important final result, for example, a theorem, a mathematician needs to prove some intermediate results, such as a lemma. And if the intermediate result is useful enough, then the researcher can decide whether or when to publish it. The benefit of publishing it now is to claim some intermediate credit. However, the cost of publishing it now is that other researchers may be able to use the intermediate result and prove the final result earlier than our researcher does. So we study when would a researcher disclose an intermediate result. And if the final reward for the final result is higher, for example, if the final result has more impact or potential, then does it mean that researchers would disclose the intermediate result earlier or later? And does it mean that researchers will be able to discover the final result earlier or later? And finally, if we force researchers to, if we impose mandatory transparency, that is, we force researchers to disclose their intermediate results immediately, then does that speed up the discovery of the final result? Regarding the first question, we find that whether a researcher discloses immediately or later depends on the environment. Regarding the second result, we find that if the final reward for a final result is higher, then researchers disclose intermediate results earlier if and only if the final reward is low. In other words, heavily rewarding final results can speed up disclosure and discovery if and only if the final reward is not too high. And regarding the last question, we find that mandatory transparency is good if and only if the final reward is sufficiently high. Let me move to the model. First, we study, the model we built is continuous time. There are two players. Each player has an identical two-step project. In order to work on step 2, a player has to achieve a success in step 1 first. So the project is sequential. And at each point in time, each player chooses how much effort to allocate in their project. The cost of effort in step 1 is linear in a player's own effort, so some cost C times effort. And for simplicity, we assume that the cost in step 2 is 0. Our result would generalize if we assume positive effort cost as well. Given player's effort, successes of each step arrive at Poisson rate. So for each unit of effort for a given player, the arrival rate of a success in step 1 is some gamma, and the arrival rate in step 2 is some lambda. After a player has succeeded in step 1, then that player can decide whether to disclose it. The key assumption that we assume is that if he discloses it, then the other player can immediately copy it and succeed in step 1. The price allocation is winners take all. So for the first, for a success in step 1, the first player who discloses a success in step 1 is going to get some price F, and the first player who discloses a success in step 2 is going to get some reward S. We assume players discount future payoff with a discount rate R. And we assume that past efforts of players' private information. So first, to simplify the analysis, in our setup, once the player has entered step 2, and because effort cost is 0 and there's positive chance of winning a reward, so that player will just exceed the maximal amount of effort, which is 1. And since that is the last stage of the game, each player will just immediately disclose a success in step 2 when they discovers it. So once a player enters step 2, what they are going to do is fixed. They're going to exert maximal effort and disclose their final success just immediately. So in a sense, after a final success occurs, the game ends. Let me further simplify the analysis. So before the final success occurs, there are 2 kinds of public histories. So the only thing that players can observe in our setup during the game is whether a success of step 1 is disclosed or not. So the first kind of public history is that a disclosure of a success in step 1 is made. In this case, both players enter step 2. The second kind of public history is that no disclosure has occurred. In the first case, what players are going to do is fixed. So both players are going to put maximal effort, which is 1, and they will disclose their success in step 2 immediately. And as a result, players' expected payoff, once they are in this stage, once a disclosure is made, is denoted as some letter U, where lambda S is the expected payoff per unit of time divided by discount rate, and 2 lambda is the total effort, which is the rate at which the second success arrives. That is the rate at which the game ends. So after disclosure is made, what's going to happen is fixed. And if no disclosure has occurred, then there are two kinds of private histories, depending on whether a player has succeeded in step one. So the first is player hasn't succeeded in step one. Then in this case, this player needs to decide how much effort to put in the project. And the second kind of history is that a player has succeeded in step one. In this situation, she needs to decide when or whether to disclose her success in step one. So these are the two things we need to figure out in equilibrium. So in the future, from now on, whenever we mention disclosure, we mean disclosure of a success in step one, since disclosure of step two is always immediate. And finally, our equilibrium notion is symmetric perfect Bayesian equilibrium. And since our presentation is short, so I'm going to skip the definition of strategies and the equilibrium. I would just move to equilibrium. So in this game, there are potentially many symmetric equilibrium. However, there are three kinds that are simple. So let me represent the three kinds of simple equilibrium. The first kind is one extreme, which we call immediate disclosing equilibrium. So in this kind of equilibrium, each player would just disclose their success, the intermediate success, immediately after they achieve it. The second kind of symmetric equilibrium is the other extreme. This is when we have non-disclosure. So a player never discloses a step one success before they succeed in step two. And one thing I want to mention is that, so in this case, each player would just disclose their step one success and step two success at the same time and get both rewards. It's like publishing both immediate and the final results at the same time. And the third kind of equilibrium is something in between, which we call continuous disclosing equilibrium. This kind of equilibrium is a little bit complicated. So it has two phases. In the first phase, which happens before time t, there's non-disclosing. The players will hold their step one success if they ever gotten one. Then after time t, each player would disclose at some constant rate from time t on. So for this, another interpretation of continuous disclosing equilibrium is simply delayed equilibrium. So after a player will hold their success for some time and then disclose it at a later time. And we show that although potentially there are many symmetric equilibrium, but actually in equilibrium, only one of these can be the symmetric equilibrium. So we find that there exists, first symmetric equilibrium exists. Moreover, all of them have the same outcome. Let me present them in the following figure. So recall that the two things we want to figure out in equilibrium is first, how much effort each player devotes to the first step. And second, once they get a step one success, when are they going to disclose it? So it turns out there are two kinds of parameters that affect what they are going to do. First, naturally, is effort cost in step one, which is C here. And the second kind of parameter is the price ratio of the two prices. So this U here, we can interpret as the sort of the second price divided by the first price. So in this figure, we are fixing the first price, and just when we move along this vertical axis, we're sort of increasing the final price. So depending on the parameters, our equilibrium look as follows. The symmetric equilibrium look as follows. First, if the price ratio is very low, then we only have immediate disclosing equilibrium. And when effort cost is low, players put maximal effort. And when effort cost increases, players' effort becomes lower. So in general, as effort cost increases, effort reduces or becomes lower. And then as the price ratio becomes higher, for example, in this region, that is when the final price becomes higher in this region, then we begin to have non-immediate disclosing equilibrium. So for effort, when effort cost is higher, for example, in this region, we have this kind of sort of delayed equilibrium. Then when effort cost becomes even higher, we have non-disclosure equilibrium. So in this sense, higher effort cost means later disclosure. And when the final price is even higher, for example, in this region, then immediate disclosure disappears. We only have sort of delayed disclosure and non-disclosure. And finally, when the final reward is even higher, then in this case, we only have non-disclosure. So this is the equilibrium depending on the parameters. The key question we study is, as the final reward becomes higher, does that mean later disclosure or earlier disclosure? So first, let me introduce the key questions that we study. Before that, let me introduce a few notations. So given the symmetric equilibrium and given a final reward S, let me use T1S to be the expected disclosure time of the first success, that is the disclosure of the intermediate result. And T2S is the expected discovery time of the final result. So we want to study if the final reward is higher, does it mean that players disclose it later or earlier? And secondly, if the final reward is higher, does it mean that players discover the final result earlier or later? And finally, for a given price allocation, the transparency speed up or delay the final discovery. So let me introduce the first result. So we find that if the final reward, the reward for the final result is higher, then depending on the level of the final reward, the immediate result can be disclosed earlier or later. Specifically, we find that higher final rewards means earlier disclosure, if and only if the final reward is not too high. Whereas if the final reward is too high, then higher rewards can mean later disclosure. So let me represent this in the following figure, or explain it in this figure. So in our setup, an increase in the final reward has two effects. The first is that it's an increase in the final reward. The first disclosure is like sharing the final reward with the opponent. So if the final reward becomes higher, then a player would be less willing to share the final reward with the opponent. So this means that an increase in the final reward has a negative effect on the disclosure. It's going to discourage disclosure. That can be found in this region when effort cost is low. In this case, players' effort are just going to be 1 in the first stage. So we can see from this figure, as the final reward becomes higher, we move from immediate disclosure to delayed disclosure and then to non-disclosure. So the higher the reward, the less willing a player is willing to share that reward with the other. The second effect of the final reward on disclosure is that the higher the reward, the harder the opponents will be working on the first step. This means that at each given point in time, if the reward is higher, then the chance that the opponent has achieved a success in step 1 is higher. So this means that the chance that the opponent is going to preempt a player for the intermediate success, intermediate reward is higher. So this effect encourages a player to disclose earlier. So this can be seen from this region. When effort cost is very high, then we only have non-disclosure equilibrium. Oh, it actually cannot be seen there since it is non-disclosure equilibrium. But in a sense, as the opponent puts more effort, the preemption risk from the opponent is higher. This would speed up disclosure. So when effort cost is in this region, then we find that when the final reward is below this yellow line, then increasing the final reward is going to speed up disclosure. Whereas when the final reward is very high, then increasing the final reward will just delay disclosure. That's the first result. I'm going to skip this. Our second result concerns the discovery time of the final result. Our question is, if the final reward is higher, does it mean that players discover it earlier? We find that the effect is also U-shaped. So higher reward means earlier discovery, if and only if the reward is not too high. Whereas if the reward is too high, then higher reward only means later discovery. And let me see whether I think I'm running out of time. So I just maybe use 1 minute to explain it. The reason that we have this U-shaped effect is that an increase in the final reward has two effects. The first effect is that it's going to increase players' effort in step 1, so that is going to speed up discovery. However, an increase in the final reward may slow down disclosure. That would slow down the final discovery. And it turns out when the final reward is low, then only the first effect is around. So it's going to increase effort and speed up discovery. Whereas when a final discovery is very high, a final reward is very high, then it's only going to delay disclosure and has very little effect on effort, and therefore it will slow down discovery. And our last question studies whether forcing players to disclose their intermediate result is going to speed up discovery. And we find that the result also depends on the level of the final discovery. So this T2 here, MT here, is the expected discovery time of the final result under mandatory transparency. So we find that mandatory transparency is good. That is, it's going to reduce the discovery time if and only if the final reward is sufficiently high. The reason is that there are two effects that mandatory transparency induces. The first effect is that it just get rid of the disclosure delay, which is good. The second effect is that players now have a higher incentive to free ride on each other's effort for the first step. So when the final reward is high, then in this, when the final reward is high, players' effort are high anyway, so free riding effect is low. So in this case, mandatory transparency is good because it get rid of the disclosure delay. Whereas when the final reward is very low, then in this case, the effort or the free riding effect is very strong. In this case, mandatory transparency will just increase free riding and reduces or lengthen the discovery time. So that's all of our results. And since I'm out of time, I'll just stop here.